And then I'll finish off with a recap and then talk a little bit about this Polar 25 program if there's time. All right. Okay, let's get started. So I like to start here when I'm giving overview talks lately. It's just very nice to see this science, this climate science acknowledged through the Nobel Prize, and in the context of the three prizes that were given that year in complex systems and the mathematics of stochastic variability in climate, and then the climate modeling through Parisi, Hasselman, and Manabe. And this is, of course, very close to the heart of people who worked in the sphere of geophysical fluid dynamics laboratory in Princeton. And I like to start here because of just the amazing predictions that were made so long ago. This is a paper that's now 50 years old, rather, from Manabe and Weatherald, taking this a very simplified representation of the ocean and land configuration, the first comprehensive general circulation model. Lots of processes were missing, but really attempt to realistically capture the atmosphere interaction with the land and to some extent the ocean surface. Looking at the response to the doubling of CO2, doubling of carbon dioxide 50 years ago, showing that at the poles, so the poles on the left here, get a considerable amount of warming and general warming throughout the troposphere, and then this signature of stratospheric cooling. And I like to think about this. This is a problem set exercise I set for our sort of introductory graduate course in atmospheric science, is just to take a couple of decades out of one of our reanalysis products or reconstructions of the last few decades of variability. And this is not a very robust or statistically sound analysis, but just take 2 decades and compare them. Take the 2010s onward, compare those to the 1980s. This is zonal mean temperature. And you can see this signature, which is arguably human influence of carbon dioxide, polar warming, stratospheric cooling, tropical subtleties in the tropics that might be discussed. But basically, this is the amplification of the climate change signal in the polar regions, also subtly as well in the southern hemisphere. And this is in a model that doesn't have an interactive ocean, but when you add an interactive ocean, you get this result from I think the work probably started in the mid to late 1980s. So this is a full maybe 15 years later. This initial prediction of the transient response to increase of CO2, which doubles after 70 years, with initial structure that also reflects Arctic amplification in this case. This is the zonal mean surface temperature as a function of time and latitude, and showing this strong signal of Arctic warming and reduced warming that goes into the southern ocean, over the Southern Ocean, and then increased warming here. And it's really striking to think that this paper came out in 1989, the Stauffer et al. It's 1989, and if I'm not getting the history too badly, there was no evidence really that there was significant polar amplification going on. This was a prediction, and the prediction was that at some point, whatever you thought of the realism of this particular simulation, there would be some sort of pattern of climate change that would look like this. So I think this is really striking, and I think that merits a prize. that definitely merits a prize, and I think it merits the Nobel Prize's use of physical principles to do these kind of predictions in the presence of a circulating ocean. You get this lag, and you get this very, very strong structure. So it's really predicted decades in advance, and we've seen it borne out in the observations. The Arctic is warming. Initially, we talked about doubling of the Arctic warming compared to the rest of the globe. Now it's 4 times. We can argue about the exact factors, but this polar amplification is real and is caused by human influence. And there are obvious implications for polar change overall. This showing the glacial mass balance, reduction in mass of the ice sheets, commensurate change in sea level. And the statements now that as we account for oceanic change, there's unavoidable increase in ice shelf melting in different parts of the world, or in different ice caps. And there's also implications for sea ice, and I'll be speaking about sea ice a fair amount. This is maybe well known to many of you, but not all, I guess. This is from the National Center for National Snow and Ice Data Center. showing this year-by-year evolution of the Arctic sea ice extent as a function of month, and Antarctic sea ice extent. So you see these opposite seasonal cycles, and the gold colors here, the sort of initial earlier part of the record, and we go to black, which is the later part of the record, and the extremes, the lowest sea ice minimum years in both the Arctic and Antarctic, are shown in red dashed. And here are some maps showing this really huge change in Arctic sea ice going from this is a typical year like 1980. And this is 2023, so last year, September 2023. And then last year was a big surprise, 2 years, I guess now we're getting 2 calendar years away. In Antarctica, we have this really striking reduction. Doesn't look quite as dramatic in the figure because of the nature of the Antarctic sea ice distribution, but this major reduction in Antarctic sea ice, and you can really trace that going from a sort of 1980s period to 2023 last year. And an unpleasant surprise because we were used to Antarctic sea ice being very stable in a sense and not varying very much. And that was part of the initial predictions as well. And here we have this standout year that we're still trying to understand in red dash. In 2024, I believe, is shown in the black here. And all this is happening, it turns out, a little faster than forecast. So the Arctic sea ice retreat is actually something that's subtly not fully simulated by these Earth system models, and that's still true today. So we have polar amplification, I'd say, is long predicted, but like many things, imperfectly understood. That's a very high standard to have perfect understanding. But I went back and forth between not well understood and almost perfectly understood. I would say it's imperfectly understood. So we have this coupling between the different signals, different parts of the change. So models this is a set of results from a recent models from CMIP6. If you can see that the models that tend to warm up the most in the globe globally tend to have the greatest reductions in the polar equator temperature gradient. That's kind of driving the atmospheric heat engine in a sense. And so there's scatter here, but effectively we see that models that warm up the most tend to have the strongest polar amplification. But even if you account for the global warming signal, this is actually a slightly different generation. This is CMIP5 models taken from Doug Smith's paper in 2019. It turns out that the Arctic and to some extent the Antarctic regions, but the polar regions are really where we have the most uncertainty per unit warming of the globe of what climate change will look like. So polar amplification per level of warming is model dependent. And so we still don't have a full understanding if these models represent a theoretical understanding of the science. We still have a weak understanding in some sense of polar amplification. And I'd say that a simple way of understanding that uncertainty is by looking at all the feedbacks involved. This is one figure I don't have time to explain, but there's been a lot of work systematically and quantitatively figuring out the effects of different feedback processes through radiative kernel techniques, basically linearizations and constrained numerical calculations, how lapse rates, the lapse rate feedback, the Planck, the basic radiative feedback, albedo, and other feedbacks listed here affect the level of Arctic warming compared to the level of tropical warming. So this is a simple measure of Arctic amplification is distance, the perpendicular distance from this line. So lapse rate feedback really contributes greatly to the asymmetry or the polar amplification. It changes in atmospheric heat transport less so. And this feedback analysis is actually quite model dependent. So this paper from Nicole Feldl, which dug into some of these effects, shows the results from different models. And I don't want to go into too much detail here, but other than to say that there's actually a lot of method dependence in these assessments. And just for the purposes of this talk is to say that there is a lot of effort to try to understand what is driving polar amplification and the level of disagreement across simulations. And what Nicole found in this study and others is that there are strong couplings between the different feedback processes. So our attempts to separate them are really confounded by obvious couplings between polar heat transport and lapse rate feedbacks in different parts of the atmosphere. I will return to these ideas here. I think one key thing is to understand that there's a lot of work to be done to understand the lapse rate feedback in more detail in the tropics and high latitudes. And these, I think I'll skip these two slides, but they really speak to how much polar amplification there is per level of warming and compared to observations. And it's actually, and particularly on the role of sea ice. But I think just to make sure that we have time to talk, oh, actually, I don't want to rush too much. So, but what I'll say is summarized in a couple of slides. So I'll come back to these graphics if it comes up in discussion. But I did want to sort of move from the topic of the causes of polar amplification and the drivers of our uncertainty to also talk about the consequences of polar amplification. Because if anything, this has become kind of a leading driver of a lot of the discussion around climate change. What does climate change look like in the mid latitudes, and how is it influenced by what's going on in the polar regions? Is that a useful way of framing the climate discussion? And I think some of the reasons for this interest is that as time goes on, we still have cold weather. That it's not like the process of global warming is anywhere near as steady as might have been indicated in this kind of figure. We have lots and lots of both warm and cold extremes, and so there's been some attempts to understand the role of atmospheric dynamics in this and the role of polar change generally. And this has given rise to a huge amount of literature. These references are a bit dated, but I mean, just to give you a sense of the interest, whether if there's links between Arctic amplification and measures of extreme weather in mid-latitudes. Does Arctic warming change the mid-latitude jet stream? Can it? Has it? Will it? And other papers along this line. Here's a way of sort of including everybody by saying divergent consensuses. So it's not even divergent consensus. There's multiple consensuses and they're divergent. So it's really hard to understand what that means. But I think there's some sort of clusters of understanding in this weird space of scientific inquiry. So the linkages between polar amplification and global warming are important to figure out, I would say. Because if we could constrain polar amplification, we might be able to better constrain some of the questions about the consequences of polar amplification. So just to kind of recap this introduction, is that just to say polar amplification was long predicted as a fingerprint of global warming, that patterned effect. And then as we get into quantitative understanding, we see it as the causes of Arctic amplification, including the role of sea ice loss and cryospheric change remain uncertain. And what I skipped showing you, but it could come back to, is that generally speaking, the models show different sensitivities that are than what is observed. By sensitivities, I mean the degree of change in the polar regions per degree of global warming. So models underestimate Arctic sea ice loss per degree of global warming, and that still holds true for CMIP6 models, so all the way up to the most recent generation. And they actually overestimate Antarctic sea ice loss, but it's interesting because the Antarctic has suddenly started changing, and that's something that this statement could actually be modified in the coming years. We don't really know. And they don't agree on the degree of polar amplification. And then just finally, that the consequences of Arctic amplification are potentially far-reaching and remain definitely a topic of debate. Whether they're of scientific interest or just more media interest is still, I think, something to be decided. I think this is actually a valid question and quite interesting. So this is where I kind of wanted to set up the research area, and so what we try to do in my group, and we've been doing this for about 10 years, is to look at coupled system models and deliberately intervene in them to induce polar amplification and see what the response to those perturbations are. It's really actually, in some ways, it's simple to describe and actually not that hard to do, but it seems to be hard to do well. So that's, I would say, or do in a way that's convincing and leads to robust results. And so this issue of robustness and trying to understand at the heart of a bunch of different simulations I'll introduce to you next is whether there are ways of post-processing or post hoc analysis that would allow us to better understand the role of Arctic amplification and Antarctic change as well in the climate system. And I'd argue that this pattern scaling analysis that we've done that has given us some insights that I wanted to share. So that takes me to the heart of the talk, and I'll just talk about the protocols first. So just schematically, so what we're doing is we're artificially inducing polar amplification. Um, so there are different sets of simulations here, and I'll try to give an overview and hopefully not confuse everybody. So what we have is this input, which is the increasing CO2 over time, right? Represented here with the Mauna Loa time series. And this gives rise to a classical response, now classical, right? 50 years going now, of Arctic amplification, tropical upper tropospheric amplification of the warming signal. I'm sorry, this is the zonal mean temperature change as a function of latitude and pressure, altitude, for a strong forcing scenario in the future, taken from the fifth assessment report, now 12 years ago. So we have cooling, stratospheric cooling, tropospheric warming, amplified Arctic warming, a little bit of warming in the southern and in the Antarctic, and tropical warming. And from this, we run the model. This is what I call a free running coupled ocean atmosphere model or system model. And from that, we extract the sea ice from it. So this is one way we can induce polar amplification. It's not the only way, but this is the way we've been doing it in my group. We take out a signal of the Arctic. So this is the change in Arctic in September Arctic sea ice that results from the global warming signal. So there's no ambiguity here. This is purely model driven. And from that, we take what we do next is substitute this perturbation into another climate model simulation. So that's what I mean by inducing polar amplification. So we're taking the sea ice loss and we're imposing it as a boundary condition. And there are different ways to do this and different setups you can do. So I'll start on the right here. This is taken from Clara Desser's work. So there's lots of pioneering work in this that goes back, but I'd say Clara's papers kind of deal with the model hierarchy in the best way, starting from 2015. And in one case, you can take what we call an AMIP type model, or just our atmosphere only model, and we change the boundary conditions. So we remove the sea ice. And what we see is a pattern of warming. Again, this is zonal mean temperature change in response not to CO2 changes. CO2 is held fixed. So there's no change in radiative forcing here. We're just changing sea ice. And here's an atmospheric response only. An atmosphere response in an atmosphere only model. The climatological temperature is shown in contours and the response is shown in the shading. And then we have a dynamical ocean on the left. So there's a big difference in the response of the atmospheric temperature, as a function of latitude and pressure, when we have an interactive ocean on the left, and we prescribe the sea surface boundary conditions on the right. And so what we learn right away from this is that our understanding of polar amplification really depends on the nature of the platform we're using to study it. All right. So what we see here is both responses are understandable in a sense, but really understanding what's going on here requires kind of a deeper thought. So obviously, there's a lot of trapped warming in both cases, all right, but and that trapping is really related to the stratification in the Arctic, very strong thermal inversion that really keeps signals of warming close to the surface. There is a stratospheric signal here. This turns out to be quite variable among different models. But when you introduce a dynamical ocean, that allows the ocean to respond and thereby drive a kind of the rest of the global warming process. So Clara called this a mini global warming. The actual strength of the warming here is relatively weak, but there's influence of this Arctic change in sea ice all the way into the southern hemisphere in this study. So simple point is that the response we get depends on the ocean model. With a dynamical ocean, Arctic sea ice loss causes additional Arctic warming, tropical warming, and even Antarctic warming. And this additional Arctic warming is important too, I believe, because what we see here is that in response to what's being imposed at the surface, you get this a deeper warming. And we argue in a couple of publications that this deeper warming is really connected to the mid-latitude warming that arises because you have this interactive ocean response. I'll show a little bit more evidence for that later on. Okay, so that's kind of a basic overview of the simulations, and these simulations really took off in the sort of 2015 to 2020 period, including work coming out of my group, but also several others. And what arose were a bunch of different modeling groups that approached this in different ways with different forcing approaches, different sea ice approaches. These were all models, for the most part, all of them used sea ice loss as kind of the driver of polar amplification. So James Green wrote a paper about this, a review paper, talking about consistency and discrepancy. So what's done here is to normalize the surface temperature response with the North Pole on the left per unit sea ice loss. Because different models had different amounts of sea ice loss, and what you see here is a pattern of warming, and some of the models show more tropical warming, some less, but they show basically consistently deep response that goes away from the surface up into sort of the mid troposphere in a sort of reasonably consistent way. But they're not all the same, and there are major differences actually in the tropics and in some of the teleconnections, the connections between the hemispheres that are established in these simulations. Um, so that's okay. And then what we also has really come to light in the last few years, starting with a paper by Mark England and others in 2022, is that if you really study this problem more carefully, this trick that I showed on the last slide of imposing sea ice loss, it drives an awful lot of Arctic warming. And Mark made the point that this probably overestimates the role of sea ice. We use sea ice as the driver, but it overestimates the role of sea ice, and in fact induces far too much Arctic warming in isolation from the rest of the global warming process, and maybe over attributes the warming process to local drivers, and that's in a sense by construction, but it didn't have to be that way. But that's how it turned out. So the concern then is that when you look at what he estimated as a true sea ice effect based on an energy balance model calculation, you would get sort of a warming in surface temperature of about 2 degrees or so using kind of standard forcings. And when you added that to the global signal, which is shown here in black, again coming from an energy balance model, but it would, you get a certain amount of polar amplification, and these model simulations, and this represents various different protocols applied in this EBM, would give you a lot more warming, and so this was he called this a spurious effect, and what it did is it torqued our interpretation in sort of the wrong direction. So there's some problems there because we're using these models these experiments to understand things, and they really mislead us in the very regions we're interested in. Then we have to revise our methods. So what I want to argue today is that there are approaches to try to correct for this and get more insight. And what we've been doing for a few years, even before Mark's paper, was to do a pattern scaling approach. So the idea of pattern scaling is simple. Is that the idea is that the regional responses across many variables in climate are linear are linear, first of all, and could be well characterized by the total level of warming on the global mean. And one nice demonstration of this from Claudia Tibaldi and Julia Arblaster comes from just comparing the pattern of response under different forcing scenarios per level of global warming. And you can see that basically there's a robust, not just in terms of land-sea contrast, but a robust pattern of response, kind of independent of the nature of the forcing and some of the timing. And there are differences, of course, but there's a lot to be learned from those differences. So this whole conversation around levels of warming, 1.5 degrees of global warming, 2 degrees, and so on, that really also relates to this idea of using the level of global warming as kind of a shorthand for how far we are in the global warming process, and then what the consequences are for different climate impacts on the regional scale and different socioeconomic impacts as well. We're looking at this method, and we've modified it to think about this variability across the pattern of Arctic warming as well. So we're using multi-parameter pattern scaling, and I want to summarize it in a slide or two. So the idea is for multi-parameter pattern scaling is that we posit that there's some dependence of a variable on internal scaling parameters. So for example, here I have the zonal wind at some location, zonal mean zonal wind as a function of T, the global temperature could be, and I could be some measure of ice. And the contours here represent the variability of U on these internal scaling parameters. We don't know what this space looks like, this landscape of how U varies, but we can use Earth system models to learn the structure, and maybe different models will have different underlying structures. But then just a simple, Taylor expansion would say that if you're looking at how U varies for a given perturbation of temperature and ice, you could separately attribute the change in U to the change in temperature and the change in ice, just using Taylor expansion there. So that's the basic idea. So the three steps to this are that we posit that a given field depends linearly on internal scaling parameters, at least locally linearly in this kind of parametric representation. And we have choices of these parameters, and that's the key point. We can choose global mean temperature, we can choose sea ice extent, we can choose different variables. And that this dependence is intrinsic and it's independent of the nature of the forcing of what took you from this initial state, which was colder and had more ice, to a final state that was warmer and had less ice. But we can estimate these from the simulations we have. So the idea is we have these responses that we observe from a bunch of different model simulations. We assume that there's good sampling, so we're not trying to account or use internal variability as a way of probing this. This relates to sort of the long-term climate response. We diagnose these parameters like this global mean temperature, sea ice extent, simple scalars like that, and we have enough information to then estimate these kernels, this variation of Z with respect to each of the scaling parameters, just based on these simulations. So that's the idea in a nutshell. And we applied it to a few. And the reason we did this is because we had both free running simulations and and these artificial polar amplification simulations. And we were having a hard time figuring out how to relate them to each other when they were forced in such different ways. So Russell Blackport and I worked on this, and we wanted a way to combine what's here on the upper left. This is a standard forcing scenario, response to greenhouse warming, and zone mean temperature. So I've shown you pictures like this before. This is from the equator to the pole. And then we have experiments where we change the sea ice albedo to induce sea ice loss. So we made the sea ice darker, and that interacting with sunlight led to sea ice melt. I'm not showing you the outcome of all those experiments in detail. But the point is they were very well sampled, and we got a pattern of response that was with strong Arctic amplification and a bit of tropical warming as well. And we wanted to try to understand what part could be attributed to the changes in temperature, in this case, low latitude temperature, and the changes in ice. So we did this decomposition. This is from 2017. And what we did was try to reconstruct this, use these two experiments to break down the total change into a part associated with low latitude temperature change and sea ice change. I didn't say this, but these sensitivities aren't observable. They're just ways of explaining what we're seeing. It's all diagnostic or a posteriori. So what we learned here is that we could, if we did this trick, we could actually take the observed change in temperature and change in ice and explain and decompose this signal. And it got a little more interesting when we started looking at dynamical quantities. So this is the change in zonal winds, and what we noticed in the CSM response is that the change in tropospheric winds is very weak under greenhouse forcing. There's a lower stratospheric change, which we can explain radiatively, but there wasn't really much going on in the troposphere. But when we imposed the sea ice change through albedo loss, we got a fairly pronounced equatorward intensification of the winds of the jet stream. And so we used our decomposition to try to better understand this lack of signal. And our understanding was that there was a negative feedback, that the sea ice response that's present here is actually trying to push the jet equatorward, and the tropical warming is pushing the jet poleward, and there's a tug of war. And so using this decomposition, we got out this answer that this lack of response is actually two counteracting effects: partial response to low latitude warming, showing as a poleward intensification, and the partial response to sea ice loss is it's a amplification of this pattern, basically, an equatorward intensification. So that was our interpretation. And we took it farther, as one will. Once one finds a tool, one uses it all over and over. So Stephanie Hayes' work as a graduate student, was to look at many of these different simulations. We had 5 different models, different protocols, and try to combine this information. So she was able to assess the response of temperature, the map of temperature to sea ice loss versus low latitude warming. So polar amplification here is really strongly attributed to sea ice loss. And there's actually a bit of attenuation in polar regions, but a lot of surface warming coming from the low latitudes. And we can apply this to sea level pressure. So there's a strong low that's agreed on by many models as a feature, and we attributed that to sea ice loss, this intensification of the Aleutian low. And other features, right? So there's actually interesting patterns here in the precipitation. And they're quite distinct. We were trying to understand how separable these signals are, and we've done some work in that direction as well. We've taken this even further to look at another full set of simulations that Steph ran, which included both Antarctic and Arctic perturbations. So she perturbed Antarctic surface albedo separately from Arctic surface albedo. So, and we recombined several simulations to actually do 3-parameter pattern scaling. And in this case, the parameters were Antarctic sea ice extent, Arctic sea ice extent, and tropical warming. So what we learned from this is the change in temperature. This is the change in zonal winds from one of these Antarctic perturbation experiments, right? So this weakening of the jet stream in the polar regions is one of the features, and there's a localized signal that's attributed with our methods, albedo darkening in the southern hemisphere, and we decompose that into a part associated with the sea ice change. Right, so this attributes the local warming and the weakening of the jet to the sea ice change. A part that's associated with the tropical warming induced from the sea ice change. Okay, and that gives you this increased lapse rate, and a bit of a counteracting signal. And there's even a part that a little bit that's attributed to the Arctic response to this Antarctic warming. And we can push it farther. We looked at we did the same kind of idea, applying this same technique to the oceanic responses. So this is the zonal mean ocean surface temperature, temperature response to Antarctic sea ice loss. And the surface is on the right, all right? And it's the same kind of decomposition. So we broke this up into a part associated with, so much of the warming signal that descends at depth here in this model, and this is the CSM1 model again, is attributed to Antarctic loss, but that extends well into the tropical regions, right? So this is a direct response from the Antarctic sea ice loss, impacts and stratification that extend into the northern regions. And we see some of the same kind of signals. So this minimum warming that's here through this pattern scaling is attributed to an associated cooling signal that comes from Antarctic ice loss. So this is all, it's not fully verifiable, but this is suggesting hypotheses to look into using this pattern scaling analysis. So before I go on, I just want to say that this is where we've been for a few years, and we're thinking about where to take the work next. And one of the issues that's come up is this issue of spurious warming induced by these very strong changes we're imposing. So we came back to that, and this is where Luke's work came in. And what we were trying to do, and this is work that's not published yet, but we're sort of getting up to date, is that the point being, perhaps not surprisingly, that the results of a multi-parameter pattern scaling depends on which parameters you use. Right? And so we wanted to see if there were ways to select these parameters a bit more strategically. So what we found, this result that we were very excited about in 2017, I think we've been forced to revise it a bit, because these experiments we've done really exaggerate the role of sea ice and the role of Arctic amplification in isolation from other processes. And what we found was that we get this really strong tug of war, the idea that the Arctic is giving rise to a very strong negative feedback on circulation changes in the mid-latitudes. And I think at this point that's actually a bit misleading. The strength of this tug of war, it might be exaggerated. by that particular analysis, and other papers have done similar things, and we're not the only people to do sort of combined signals. So I hope I didn't give you the impression that I thought that, or even that was the state of the science. But this tug of war is perhaps this idea that there's these very strong negative feedbacks, I think, is a bit exaggerated, and I'll show you evidence for that in the last few minutes. So we've come up with a couple of different ideas to address. First of all, just to see if the results are really sensitive or not to our choices, because if they are, then that says we haven't quite finished our work to try to really explain what's going on and how Arctic amplification can, it figures in an isolated way in the rest of the problem. So the two additional methods that we've been working on involve some estimate of the forcing that comes about because we've imposed changes to sea ice artificially. So there's a radiative forcing associated with those, and every protocol approach, whether it's a nudging approach or a change in albedo, has its own kind of artificial effects that come along with it. So what we try to do with the sea ice forcing scaling is to measure the induced radiative forcing from changing sea ice in an artificial way. And so what's not so important is exactly which temperature variable we use. So we generally use low latitude temperature, but we could also use global mean temperature. But it's the second parameter, the ice loss versus using some measure of the forcing, that actually changes the results a bit, as I'll show. So this F-PERT is it's hard to estimate. In a setting of an energy balance model, Mark England showed how to estimate it, and so we took that and have used that. But actually, for some of these protocols, it's quite hard to figure out what exactly the radiative forcing is that goes with our sea ice loss method. So it involves a lot of work. More recently, though, we were thinking about alongside Nicole's work, which we were loosely involved with. So she figured out that there were actually ways of breaking up the response to the lapse rate that showed how lapse rate and heat transport effects were coupled. I'm speaking very very loosely here just to save time. But the idea is that you can actually look at the deep response of the tropical lapse rate to global warming, which is very robustly estimated across models, and then also incorporate the change to the lower tropospheric lapse rate in polar regions as a kind of as a measure of local polar change, and that's basically based on the argument that there's a density surface or an isentrope, in fact, a moist isentrope that separates the lowest layer, the lower world that's in contact with the Arctic surface, that extends to the mid-troposphere in polar regions and down to the mid-latitudes. That's a sort of a separate layer which is very strongly influenced by Arctic processes. And then sort of the rest of the system, lower latitudes and the mid-latitudes above, say, 400 hectopascals, above 0.4 atmospheres, is more connected to the tropics. So this lapse rate scaling is based on those ideas, and it turns out that lapse rate scaling, this divided lapse rate approach, or this separation, is really useful for the feedback analysis I showed you way back here. Okay, so this new estimate of lapse rate feedbacks is actually something that was explored in this paper and actually led to an important revision of the role of the combined water vapor and upper lapse rate feedbacks. So with no more than that as motivation, I suggested to Steph that we use the lapse rate, the tropical lapse rate as one measure, and then the lower Arctic lapse rate as another measure, and she went ahead and did the Antarctic lapse rate as well, which I thought was a good idea. And so that's part of her paper. But what I'm going to do now is actually compare these three methods, and this is some work that Luke's been up to, and I wanted to share that with you. So, okay, I know that's a long setup, but there are these three methods. And what we have here are three different experiments. I'll have time to show maybe two. So this is a modified albedo experiment with the CSM model. And I've shown you figures like this before. This is the response to doubled CO2, and this is the response to change of albedo on sea ice albedo and also bare ice albedo. And I've shown you these patterns before. This is the raw responses. And then these are various multi-parameter pattern scaling decompositions. This one is based on sea ice extent scaling. And I want to draw your attention to this little cold spot here. This actually says that if we take this at face value, we say somehow that tropical warming is driving Arctic cooling, and that doesn't really make much sense. So it actually this gives you tropical amplification, and that's always been a suspicious feature. And what this big bite here, basically this is something that is being attributed to ice loss. Okay. If we use sea ice forcing scaling or lapse rate scaling, the picture changes quite a bit for this model. And what we get is that some of the tropical driving is actually leading to a lapse rate change that is involves a connection between the mid latitudes and the Arctic. So and this is, although this is the response to tropical change, and this is the response to the sea ice forcing, including the albedo effect that changes the shortwave. This is giving a bit of a nuance here. It's getting rid of this little feature here that actually ends up being pretty important for the tug of war argument. And what's interesting is that if we use lapse rate scaling, it's a bit of a combination of the two above, but basically the lapse rate scaling is giving a similar picture to the sea ice forcing scaling. And the lapse rate scaling is much easier to calculate, and we think has a sounder physical basis for being a driver of real variability and change in the polar regions, as opposed to directly measuring the sea ice only, where we're actually changing and intervening in the model. So that's one example. And then we looked at some other simulations. So this is from for a very different type of forcing regime, and it's actually a different model. It's the older version of Wacom of CAM with a high top. Point is that we're getting basically similar picture, that sea ice extent scaling attributes all the Arctic warming to sea ice change. But if we use the forcing scaling, or if we use lapse rate scaling, we get a bit more nuance. There's a bit of Arctic warming that's attributed to tropical warming, and given that the tropical warming leads to so much more poleward moisture transport, we think that's a reasonable picture to paint, and and gives it a bit more of a role for the mid latitude poleward heat transport in driving this. So let me. I did want to leave time for questions, but let me sort of just say that we started to look at this in other simulations, and this, it turns out that the simulations give you very different combinations of patterns of response. It's not just the model dependence; it's the protocol dependence. So this is a very different method that Aguo Dai and others used, where they prescribe fluxes in a way that we think is probably not leading to the spurious warming that was seen in the other calculations. And the lapse rate scaling is quite robust, and it actually agrees with the sea ice scaling in this case. And what we think is going on is that these tests are exposing some of the spurious effects. And so again, what we're trying to do is usefully combine a free running climate model experiment with one of these artificial experiments, recombining them in ways that help add to their interpretation. So, because I guess I didn't say it, but these simulations are all very expensive, right? So every time we undertake one of them, we have to run them out to equilibrium, or we have to run a large ensemble. So we really have to use these to the best of our abilities. We didn't think about this when we got started, but now that we have so many of them, I think it's really important to use the information the best way you can. Okay, so that was kind of a run through, but just to sort of conclude, so just the key points, Manabe and others predicted the pattern of polar amplification almost 50 years ago. This is maybe a bit strong, but to say that simulated polar change does not quantitatively match observed polar change, and that models tend to underestimate. If they get the warming right, they tend to get something else wrong. So that's one of the issues that's come up. And I skipped some of those slides, but I think you get the point. And so we've probed the dynamics of Arctic amplification by inducing it in these models. And I think we're gaining insights into the separate roles of tropical warming, Arctic amplification, Antarctic amplification, which is only now really becoming apparent, lapse rate changes, and so on. And we're using the same kind of methods of pattern scaling to deal with these issues of exaggerated polar amplification in some of our simulations. And then this is a slide just about the different choices we've made on scaling parameters. So the sea ice extent scaling is really simple. That's why we used it. It was very simple to say, okay, sea ice change or local temperature change and tropical change are the two things we can compare. And that followed previous literature. But it really overemphasizes, we think, the tug of war. And it's entirely possible that in the absence of any albedo feedbacks or any sea ice change, you can still get polar amplification solely because of tropical warming, and that's through poleward heat transport and polar moisture transport with the latent heat release. So there's no reason that we need to have an either or approach in this. We're trying to find the best way to use pattern scaling, and I'm sure there are superior methods out there. And we've tried to more explicitly identify the forcing that we're introducing by trying to get rid of sea ice when there's no greenhouse forcing. This is the real issue. And lapse rate scaling is simple, and it's connected to these feedbacks, the feedback analysis that I mentioned in Feldwell. So I think this is worth pursuing. And sort of our recent analysis suggests that the last two methods are kind of consistent, but we really need to work on justifying these approaches and to relate this lapse rate to changes to sea ice forcing and get that all sorted out. So there's future work to be done. All right, so that's the results. Albion, do I have some time to plug
Yes,
Polar
absolutely.
25?
Yeah,
Okay,
yeah.
okay, all right. So I'll just take a minute or so. For those of you who don't know the Kavli Institute for Theoretical Physics, it's a center at the University of California, Santa Barbara that runs lengthy programs in different areas of physics and physical science. And we are fortunate enough to have this proposal accepted to run a program on the physics of changing polar climate. So it's running. May 13th is a Tuesday. I think for some reason it's starting on the Tuesday, but it basically the week of May 12th through to July 18th. The coordinators are along with me, Patrick Heimbeck, Gudrun Magnusdottir, Matthew Morlingham, and Elen Sarusi. And we have Matt England, Brad, Sophie, and Fiamma Straneo as advisors on this. And it's a broad program. It incorporates Arctic and Antarctic science. It incorporates oceanography, sea ice research, atmospheric research, and ocean research. And the idea is that we're interested in all these aspects of Arctic and now Antarctic amplification, the role of feedbacks, the global implications of polar change. We want to know how glaciers and ice sheets will evolve and how this depends on interaction with the other Earth system components, and questions like that, transport of energy, moisture, and constituents. And of course, relating to questions in paleoclimate, although the program's not focused on paleo per se. And what we wanted to do was try to spend a few weeks overcoming some of the barriers that we find in between the different disciplines, getting some of the different cultures together. So we have looking for common ground across these different areas, and I guess our point is that the research areas are maybe more siloed than they have to be, and that a physics institute is a good place to get together to talk about these things because we can maybe focus on the common ground and overcome some of the disciplinary jargon that sort of separates these fields. There's a lot more that separates the fields, real issues, but there are issues where we really do need to combine forces a bit more deliberately. And of course, with data science, machine learning approaches, seeking to improve climate models rapidly, this is a really good time to get together. So that's basically all I had to say on the program. I would just say that there's a basic schedule, which is that we will have the state of the science in the first block, which is about 3 weeks. And then we'll start looking at the common ground is sort of the technical advances that we think should be discussed across the different disciplines. We'll have a conference in the middle, which is part of the KITP typical program, and a transdisciplinary focus that's still being decided, but something in the applied domain. And then we'll wrap up the last couple of weeks with a kind of synthesis and attempt to pull together some of the ideas and see what new research has come about. So that's the program, and it's very heavily subscribed, so I can't invite you all to come in person, but there will be a lot of online material, and I'm hoping that there'll be a lot of ways of communicating with the program, and we're working on that. We're meeting weekly at this point to discuss the program, and look forward to seeing some of you there, and others. I'm very happy to chat with you about it. And that's it, I think, Albion. I'll leave it there.
Good. Thank you, Paul. Great talk. Yeah, in my experience, the talks are all recorded and on the KITP website.
Yeah.
You can go there.
Yeah.
Are there any questions for Paul? You can use the hand raising tool and then I can find you. While I wait just to try to get my head around the pattern scaling approach. So for one example, you have a parameter that doesn't, as I understand, it doesn't give you a realistic or puzzling response, and two that give you similar reasonable responses. So is the point that two of them are somehow have better covariance or dependence on some underlying parameter, and the other just depends weakly on that? And that or what's the
Yeah, I undoubtedly I didn't explain that well or fully, but the first approach was easy, and it was a heuristic, and we found that when we used it, when we said we deliberately used sea ice extent as one variable and tropical or global temperatures as another, it gave this really clean decomposition between the Arctic response on the one hand, and like all the temperature change was attributed to sea ice change in the Arctic, and then all the tropical warming, sort of the rest of the response, came with the other contributor. But the thing, there's two issues with that. And one is that we know it's naive and misleading to solely attribute Arctic amplification to local changes. There's a lot of literature on this, and there's a lot of controversy. But when you have locked albedo simulations or other simulations where you deliberately don't let the Arctic surface change, you can get a fair amount of tropical warming. Sorry, of high latitude warming of polar amplification solely by raising the ocean surface temperatures. And that's accomplished through poleward heat transport and polar moist static energy transport and latent heat release, which we've studied out, otherwise in the group. But the vertical structure of that signal is different, and what this lapse rate scaling is giving us is something whose horizontal and vertical structure looks a little bit more like our thinking that incorporates, some of the dynamics of poleward heat and moisture transport. So that was reassuring. The other thing is that this other issue is that these forcing approaches, these nudging or albedo change approaches, give you a lot more Arctic warming per degree of global warming than is observed, and that's by construction. And Mark England's contribution was to actually quantify how unrealistic that was, and it's about a 50% effect. And so we started to figure out, well, what artificial forcings we're putting in, and use those in the calculation, and that's this sea ice forcing parameter. So we're still. I think we're still struggling a bit with the vocabulary to use to make it less confusing, but it turned out that these two approaches gave similar results. And so we're thinking that the lapse rate as an internal measure, lapse rate changes are actually a really robust and well-reasoned measure for understanding as a parameter. It's an internal parameter, it's internally determined, but it's a parameter that is maybe naturally connected to variability across models and some of the, as a measure of internal feedbacks, it seems to work well.
I see.
Yeah, sort of long-winded answer, but there you go.
Other questions, Brad?
Hi, Paul. Nice talk.
Thanks.
I was wondering if there have been any modeling studies for stratospheric aerosol injection that have given any interesting insight into polar amplification as a different kind of forcing than the ones that you've discussed here.
Yeah, that's a really good question, and I think forcing that operates in the short wave versus in the long wave, and there's different those have not been systematically studied using this with a pattern scaling approach, and I think using this as the tool to understand the different components of stratospheric or any sort of geoengineering approach would I think make some sense. I still think that it's still quite heuristic, and so I'm not sure I think it could add value, especially if you saw different SAI experiments that had very different results. Maybe we could try to break down that dependence into more dependence that comes about because of convective processes versus sort of land surface ice albedo processes. So that might be helpful there, but it hasn't been done as far as I know.
Thank you. We have time for one more quick question.
Yeah, I have another meeting coming up. So
Yeah. Okay, if there's nothing, I think we'll close and thank Paul for a wonderful talk.
thanks so much.
And let me just say that our next March is the APS Global Physics Summit, so there will be no talk next month, but in April, mid-April, we will have Isaac Held. And then in mid-May, we'll have Annalisa Bracco. So you can go to the website for that. And Paul has dropped his email into the chat if anyone wants to contact him. And again, thank you all for coming. Thanks to Paul for a great talk, and hopefully we will.
Thanks very much. Really nice to get the chance. Bye.
Yeah.